Hey, everybody, welcome to the Module 10 NT141 lecture on lockouts and tagouts. We're going to be covering lockout, tagout, work control, configuration management, maintenance boundaries, and something called environmental qualification. So, what all these things are designed to do is they protect workers. Our whole goal here is to protect people and equipment. We want to preserve equipment configuration. We want to make sure the stuff is in the right configuration. And what that means is when we need an ECCS pump to start, the valves need to be in the right positions. The controls need to be in the right positions. All of the things need to be in the right positions. And that's configuration. We need to make sure that all these things support plant reliability and especially safety related equipment. Safety related equipment matters because we need it to be available when we need it. All right. So we're going to switch here. So that's what this lockout, tagout, work control, equipment qualification is about. And then this safe work ecosystem, right? What does it all take? We can't just have a lockout tagout program and think that everything's going to be fine. We also have to have work control and configuration control. We also have to have something called environmental qualification. And we're going to get into each of these in very specific detail. And we're going to talk about human performance tools. Basically, the lockout tagout protects the workers from hazardous energy. The work control and the work configuration ensures that the maintenance is planned, that it's been authorized, that we're doing the thing we say we're going to be doing, and that we're controlling it and coordinating it. Human performance tools reduce error during field work, and our configuration management keeps the physical plant aligned with the design bases. So together, all these things support worker safety, equipment reliability, and nuclear safety. So lockout, tagout, like I said, protects workers from unexpected energization, startup, motion. You don't want to be working on a pump and have it start spinning on you, right? Pressure release. You don't want to tear into a pipe and have a bunch of pressure released. Contamination. We had at Energy Northwest, we had a reactor water cleanup pipe that they were doing some work on, and they had an uptake event. A worker inhaled contamination, and that was pretty serious. So we want to make sure things are where we expect them to be and not where we don't want them to be, because these things can release energy when you're not expecting it. Now, electrical energy is the most obvious hazard here, right? If I'm going to go work on, in fact, one of the things I got to do, I got to replace my front doorbell. If I'm going to go work on my front doorbell, I can't just unscrew the doorbell off the front of the house. I shouldn't unscrew the doorbell off the front of the house, disconnect the leads, just make sure they try not to touch, right? And then carefully put back on the new one. That's the bad way of doing it. I've done maintenance like that before, and it's not worked out. It was a couple times. I think a lot of people have experienced really, really horrible electric shocks from unexpected energy. And that's what we're trying to avoid. But that's not the only thing. What if what's a good example? You're going to be you're going to replace the zincs on your water heaters, because we learned, right, that a zinc anode is in your water heater and it needs to be replaced. And I'm just realizing I need to replace mine. And you don't want to do that while the hot water heater is energized. You don't want to do it while it's full of water. So you have to create a safe environment to protect yourself from the hydraulic pressure, from the heat, and if there's some like an air system, pneumatic pressure, thermal energy, stored spring energy. I mean, all these things can either hurt somebody or damage equipment. So if maintenance personnel need to replace a motor-driven pump, the electrical breaker supplying the motor may be opened, locked, and tagged. Workers also consider stored pressure in the connected piping. Maybe it's filling with fluid. We got to make sure we isolate all the goes-ins and the goes-outs. So an effective lockout tagout addresses all hazardous energy sources, not just the electricity. All right, so the basic lockout tagout process follows a controlled sequence. Workers prepare for the job. Okay. Hey, you're going to go work on this centrifugal pump. You're going to go replace this relay in this system, whatever it is. You're going to go look at the prints and look at the drawings. You're going to notify affected people. They're going to start preparing a lockout tagout. They're going to shut down the equipment. They're going to isolate the energy sources. They're going to apply locks, if applicable, and tags. And then they're going to verify there's no energy in the system. And then you perform the work, you remove the locks and tags, and you restore the system to service. A lock and a tag do different things. A lock physically prevents operation of a component, such as a breaker, switch, or valve. And I have some here, like this one. Here is a lock, and it's going to have a property of, it's going to have a danger symbol on it, like that. It's going to say danger, locked out. The key is going to be controlled. And then how do we use this? Well, we have to put this in something. So if I'm going to put it on a valve, maybe I have to, I want to make sure we don't operate that hand wheel. So I have something like this, and I open this up, right? It's got the little cutouts in there, and I put it around the hand wheel, and then I install my lock through the hole here. We have a lot of different devices. Maybe I want to lock out the stem of a valve. So we've got this, and it's got holes in the top and the bottom. We wrap that around the stem of the valve, and then we lock it. We put our lock through here, and we hang a tag on the lock. Other things, some of these, we have very specialized types of locks. So this device, like there may be, there's a use for something like this, where you're going to hook it onto something like a big switch, and you're going to hook it on there. And then once this is on there, the switch can't operate. Maybe you need a specialized little scissors lock like this. You can put this around a valve stem. You can put this, well, there's lots of different examples like this. And so these locks prevent the physical operation. Now, tags convey information. So we have tags that say, danger, do not operate. And then there's maybe some information on the back. And this says, do not remove this tag. Okay. And then there's a spot to put remarks there. We have tags like this, a danger tag, do not operate. And this lock tag may only be removed by this person. And then on the back, it says unauthorized removal may result in immediate discharge. So this is put on something that says, hey, we have energy behind this valve, for example, like this says valve 101 and this says valve 100. So we put this on there because that says there's energy behind that. Here's another example. The equipment locked out by Troy Aikman and Emmett Smith, and it's got a phone number on there. And then it says this lock tag and lock to be removed only by person shown on back, like that. Now, every place out in the industry kind of does it the same, except for one. Hanford, PNNL, BPA, Framingham, all these places, all these industry places, they use locks and they use actual lockout tagout with barriers. Energy Northwest is kind of different. They just use tags, and their tags look a little different. They're hung by operators. Only operators hang tags, and non-licensed operators will go out and hang tags, and they rely only on tags. So if there's a breaker, and if you turn on this breaker, somebody could die, there's no lock on it. There's just a tag. So that's something specific to know if you ever are out at Energy Northwest, is they rely on a tagout system, which they also call clearance order. All right, let's get back to our PowerPoint here. A tag communicates information. It identifies the clearance boundary, the tagout boundary. So tagout and clearance, those are interchangeable. We're saying the same thing when we say clearance. It warns workers not to operate the component, provides administrative control. A tag alone does not provide mechanical restraint. So Energy Northwest is just administrative control. If you operate something that has a danger tag, you're out of a job. It's a no-no. So lockout tagout also depends on worker roles, and authorized workers trained and approved to apply or remove lockout tagout devices. So once again, at Energy Northwest, that would be non-licensed operators. Other places in the industry do it a little bit different, and they allow other people to do it. But either way, you're going to be trained, and only trained people can apply a tagout or clearance. Only trained people can do the second checks. Only trained people can do this zero energy. Yeah, an affected worker may operate or work near the equipment under a lockout tagout, but you can't apply or remove the devices. So somebody will be trained to apply that boundary to isolate that system, isolate that component, hang all the tags, drain the system, remove pressure, vent and drain, all that stuff for a worker to go in and do their work. But the worker, and this is what this lab is about, the worker still has to verify the boundary. They have to verify the zero energy without touching, well, what you'll touch, but without operating any of the locks or devices, without trying to turn the valves. Yeah, so that's what we're going to get into in our lab. So a zero energy verification, like I said, the tag is the warning, and the isolation doesn't prove that the equipment is safe to work on. There's a big difference between isolating something and making sure it has zero energy, right? Safe to work means energy's been verified at zero and all the hazards have been removed. Isolated just means that the valves are closed on the inlet and the outlet, the vents and drains are opened, and power, any electrical power, has been isolated. So a valve may be shut and locked, but there might be pressure trapped in the line. A breaker may be open and locked, but voltage must still be verified. Like, we still have capacitive circuits on some things. And so maybe it's a capacitive circuit and there's still energy there that could hurt somebody. Safe condition means the equipment has been isolated. Safe to work means energy's been verified zero and residual hazards have been removed or controlled. Once again, you cannot assume that isolation and zero energy are the same thing. And you will all be doing jobs where you're going to have to eventually verify an isolation, verify a boundary, verify zero energy before you put your hands in the dangerous thing and work on it. So when we do live, dead, live, and I don't have a multimeter in here, I'm going to pretend this is my multimeter. And when we do a live, dead, live, this is very specific. You have a multimeter, and it's going to be on the voltage setting, and you're going to check to make sure your voltmeter works on a live source. So if I was here at the house and I wanted to make sure that power at the doorbell was dead, I would put my voltmeter probes into the outlet carefully and verify that it shows the 110 volt. And once I verified that the meter works, right? So that's the live check. And this is a live, dead, live. So I've done the live check. Now I check the doorbell. Now I go up after having the breaker turned off, and I verify that there's no energy, that there's no voltage on the leads going to the doorbell. Okay, so it reads zero. But what we have had in the industry is people will do a live check and then they'll go verify there's no voltage and the meter dies right there. So once you've verified no voltage, you have to do a third thing. You have to do another live check. So you take it back to the voltage source and verify that the meter still works. So you verify the meter works and reads voltage. You check that the thing you're checking is dead, that there's zero voltage. Then you go back to the live source and you check it again. This is hugely important. Live, dead, live check. This proves the meter worked before and after the test. So if you had a technician preparing to replace a motor control center breaker, even after the feeder breaker's open and locked, they must still verify the absence of voltage at the work location. So the live, dead, live check confirms both the circuit de-energized and that the test instrument is functioning properly. So for clearance controls, we have multiple groups. In an outage, lots of different groups are trying to work on stuff that share isolations. So when multiple workers are working under the same clearance, a group lockout may be used. In a group lockout, each worker applies their own personal lock to the group lockbox. And then the equipment cannot be restored until every worker has removed their own lock. This preserves individual control, prevents one person from restoring equipment while another person is still working on something else and is exposed to that energy. Each worker controls their own protection. No worker should depend or rely on another person's lock for protection from hazardous energy. So we do have a lot of lockout tagout errors. I had the guy that does the investigations at Energy Northwest. I had him come and talk to my second-year operator students this year. I'm going to try and bring him back again. But he brought a lot of the things that have been happening out there with new non-licensed operators, especially. And then any new technicians that, hey, I didn't know I couldn't operate that, or Yeah, I didn't understand this boundary. I mean, lots of things can go on that happen. A tag, especially at Energy Northwest, where we don't rely on locks, right? We don't rely on these. It's just administrative. Tags can fall off. They're held on by string. Sometimes they use zip ties. A lot of times it's string. They tie them on and they can fall off. Especially if they're hanging for like weeks in an industrial environment. And so somebody will see a tag laying on the ground and then they'll throw it away. That's not the right behavior. If you ever find a tag laying on the ground, take it to the control room, tell a supervisor. Sometimes we fail to isolate all energy sources. I witnessed on the submarine, we were doing some maintenance, and I witnessed somebody working in a high pressure air compressor dryer that still had voltage in it. And they tried to pretend that there was no voltage, but you could see his body do this every once in a while. Yeah, it happens. Sometimes we mess up and don't isolate all the energy sources. Sometimes, if we have common boundaries, they'll remove their boundary without authorization. Sometimes we'll put tags on the wrong thing. So these are things that it takes strong human performance behaviors to prevent. These errors lead to equipment being energized, pressurized, misaligned, and unsafe. So a tag out walk down is not just, hey, they said I got to walk this down, but it's probably good. This is something you absolutely have to do. You have to verify component identification. We have NLOs that hang tags on the wrong thing because we have a lot of things with really similar names. You might have a valve, RHR valve 102, and then an RHR valve 102 alpha and an RHR valve 102 Bravo. And you need to hang the tag on 102 alpha and they hang it on 102 Bravo or on 102. And they make assumptions and you can't have those kinds of behaviors. You have to be, is this actually the right thing? Is it in the required position? What are all my cues for verifying it's in the right position? Is the tag, is the lock on there? If you're at Hanford, is the lock in there that such that it prevents operation? Is the tag on there such that people will see it? You have to do the safe condition checks, which means the zero energy checks. And then if you come across a discrepancy, if the required position doesn't match the field condition, a lock or a tag is missing, stop work. You stop everything and you tell everybody. You do not push on until the discrepancy's resolved. So I've been hitting on the human performance a little bit, and this is why we talk about and teach placekeeping. This is why we talk about how to use procedures. This is why we talk about what a peer check is. This is why we talk about how we communicate in the nuclear world, because all of these things really matter. And something like when we're hanging tags, when we're hanging on do not operate tags to protect one of your peers because they're going to put their hands in something dangerous to work on it, lives are at stake. And so these human performance tools support safe work by reducing the preventable errors. These tools are used because people are fallible. We've seen that. Even when they're trained, even when they're experienced, even when they think they're trying to do the job correctly, we can make mistakes. So procedure placekeeping helps workers track where they are in a procedure. Peer checks provide another set of eyes before an action is taken. I was part of an outage. I was walking around with a non-licensed operator. I was a new instructor there, and we were going out to the subyard, and he was hanging a clearance, and we were going to hang a clearance on something, and we almost hung it. Like, he had checked it. I had verified that that was the right thing. And then he was getting ready to put the tag on. I said, wait a minute, say that again. And then we looked at the label and we were on the wrong component and we both almost missed it. It is really easy to do. So being the peer checker is a very, very critical responsibility. Three-way communication. I say this. I understand you said this. That's correct. A questioning attitude. That helps workers challenge anything that's unclear, right? And when we say a questioning attitude, those words are part of the human performance tools that we use as far as, is this work safe? Are we doing the right thing? This doesn't mean be curious about quantum physics, right? That's not what questioning attitude means. Questioning attitude means, am I positive that I fully understand the scope of the work involved here and that I am going to be safe? where I am making sure somebody else is safe. And you have stop work authority. Every single person has stop work authority. If it is not safe, if you are not sure, if there is something that doesn't look right, you stop. So these are especially important during maintenance and field work because we're dealing with real equipment. We're dealing with super high voltages. We're changing, big pumps, like some really hazardous energy, a lot of contamination, all that stuff. And then one of the things you can do to help make sure all this is lined up before work begins, you do a pre-job brief. A pre-job brief is where the team gets together. And when we do a task, and we mess it up and then we do an investigation, one of the things that they find out in an investigation is, hey, we got back and we found out that only one person went to the pre-job brief. They sent so-and-so because they figured they needed to know and they would tell everybody else. That is not an effective pre-job brief. If you are part of a task, you're part of the pre-job brief. So that's where the team reviews the task before going out to the field. A good pre-job brief covers what's going to be done, what hazards exist, which steps are critical steps, how are we going to handle communication, what conditions will require us to stop work, and what actions are expected if the job does not go as planned. So, for example, if a maintenance team's replacing a safety-related valve actuator, the pre-job brief should identify lifting hazards, electrical isolation requirements, unexpected valve position. What if we find this in the wrong position? And post-maintenance testing. Hey, we're going to take this valve apart and put it back together. How do we verify that we didn't bind up the valve and prevent it from operating? We're going to take this pump apart and take the motor off and put a new motor on. How do we verify we wired it up in the right direction? And you'd be surprised at how often electricians wire pumps backwards. Anyway, so you have post-maintenance testing that has to happen before the valve or the pump can be declared operable. So discussing all these beforehand reduces the likelihood of errors in the field. And then with configuration management, this ensures that the physical plant, the pipe I'm looking at, the valve I'm looking at, the pump I'm looking at, matches the plant's drawings. You don't just trust that the drawing's accurate. You don't just trust that the plant's accurate. Well, the plant's the plant, so it just is. But you have to make sure those things match. You have to make sure the procedure works. You have to make sure your design documents and your licensing basis, all these things are in place and they work. A plant can have good equipment and good procedures, but if the equipment is mispositioned or incorrectly restored, then the safety function may not be available. And we've had this happen at Energy Northwest. Hey, we thought we had the slick system and it was isolated. Was that us? Was that another station? There was a station that had it. Found out there's standby liquid control, the thing that injects the boron in the event that the rods don't go in. Their slick system was isolated. It was poor configuration control. They didn't do a post-maintenance testing. They didn't do a system restoration after doing work on it and removing a clearance. And they left isolation valves closed. And so if they had a scram that didn't work and they needed to inject boron, it wouldn't have happened. The NRC does not like that when that happens. A lot of people get in trouble. So the configuration management helps ensure that our plant configuration in the field matches all the approved documentation. Does your work order match? Does the drawing in the work order match what you're seeing in the plant? Does it have valve lineups? Does it have breaker positions? Maybe there's a temporary modification. Does it reflect the temporary modifications? The system status, all those things. And it can get more complicated because we often use things like jumpers to bypass logic systems. We often use bypasses. We'll open a bypass valve, or, we do things that basically manipulate valves, breakers, switches, or test points outside of the purview of the control room. And so these things have to be documented, communicated, coordinated, and verified. And these manual actions can bypass automatic systems, right? We just talked about scrams, isolations, actuations, interlocks. Like, it can bypass all those things and affect safety equipment. Temporary jumpers are especially risky. If an INC tech leaves a temporary jumper in a system, they could alter the circuit behavior. They could bypass the normal system response. Yeah, so, and this is a common thing, INC techs, you'll install maintenance jumpers to support troubleshooting. If you don't remove that jumper or document it during restoration, the system may appear normal, but then when it tries to fire, when a signal comes through, yeah, then people are out of a job. Or worse, you hurt somebody. Okay, when we're establishing maintenance boundaries, that's the physical limits. That's the component or the system or the function. And these boundaries matter because the intended boundary might affect other equipment. It might create things that happen that may affect us that we're not thinking about right now. And so the workers must know exactly what equipment is included in the work scope and what equipment is not. Workers have to walk down the tagouts to find out, okay, what is the maintenance? Does this show that this is the maintenance I'm doing? Or does this boundary make sense? What are the required positions? Do these positions make sense? And then look at the tags and the valves and the breakers and see, does this match what the plan is? So a pump boundary, a pump maintenance might be going on that includes the pump casing, the motor, the seals, and the electrical interface, but not necessarily all the connected suction and discharge piping. And so if you don't understand the boundary, you may disturb equipment that was not evaluated, isolated, or restored. Make sure you work on only what you're supposed to work. So we have several different classifications of equipment, and it's going to be a little different between Hanford and PNNL, Energy Northwest. But generally, you have safety related and non-safety related. Now, some places will have something called augmented quality. So safety related is required to function during or after an accident to support safe shutdown, core cooling, containment integrity. This is, for example, all your ECCS systems, HIPCS, HIPCS-HIPSI, LIPCS-LIPSI, ADS, all these things, RHR, those are all safety-related things that are required to function during or after an accident to support safe shutdown. Non-safety related equipment, it's not necessarily, it's not credited at all for accident mitigation. If that system was removed, or incapacitated, whatever, it doesn't matter for safe shutdown. And so some examples, the obvious example is like the light fixtures. We have flashlights, we have emergency lanterns, so you don't have to have the normal lighting. But for the middle one, augmented quality, where maybe it doesn't have a safety impact, but it's still important, right? And the one that comes to mind for me with this is RICSI, the reactor core isolation cooling. It's not a safety system. It's not an ECCS system, but it is very important. It has very high importance. It does have elevated controls. And so, yeah. So you have to understand what type of equipment you're working on. If you're replacing a non-safety component, it's going to be pretty simple. But if you're replacing a safety-related or an augmented quality component, that may require specific parts, controls, testing, documentation, maybe an engineering review, maybe training. If you're going to go replace a light fixture in an office area, that's standard maintenance controls. But if you're going to work on a safety-related containment isolation valve, that requires qualified parts, qualified, tested, verified parts in engineering review, post-maintenance testing, formal operability determinations. All these things have to be in place to make sure that we're not messing up something that we need to work in a certain way. And that's what kind of this environmental qualification. So we call it environmental qualification. It is if I have this gasket that needs to be rated to an extreme temperature or extreme pressure or other extreme conditions during an accident, then we buy a special gasket. We pay extra money for a special one that goes through an EQ process. And you'll just hear EQ a lot, or quality control process. And so that verifies that this equipment or component will perform its required function under accident conditions. So those conditions may be high temperature, high humidity, radiation, pressure changes, steam impingement, chemicals, chemical spray, chemical exposure. EQ is required for equipment that is safety related. So all safety related equipment was required to have an EQ and then located in an environment that could be affected by a design basis accident. A component must not only work during normal conditions, it must work when the environment is harsh and the safety function is needed. So what is an EQ documentation? I'm going to go work on this safety component and I need this special gasket. So the EQ documentation tracks the component's design basis function, its service conditions, its qualified life, how long is it good for, maintenance history, replacement parts, and test bases. We track all those things on all our safety-related equipment. It's a lot. It's tracking a lot of stuff. And so work on our EQ equipment must preserve that qualification. That means using qualified parts, maintaining required seals and coatings, using correct fasteners and materials, and then documenting all those changes. One of the comparisons I can think of from my own experience is the SubSafe program. We lost the USS Thresher in 1963. So the Navy established rigorous controls when we lost the Thresher, because what they found is, what if we had better parts here? What if we had tracked some of these components? And yeah, I'm not going to get into all the details on the Thresher, but basically the Navy has a SubSafe system, and this SubSafe system tracks critical parts and materials. It provides traceability, requires special procedures, configuration control, inspections, documentation. That's what we're talking about with this nuclear EQ. Though they are different programs with a little bit different objectives, they have the same philosophy. If you have equipment that's going to perform a critical safety function, that safety function must be maintained, modified, and documented in a way that preserves confidence in its performance forever. So common EQ errors, quality errors, maybe we use an unqualified replacement part. And we've done that at Energy Northwest. Somebody in the warehouse pulled the wrong gasket off the wrong shelf and handed it out, and they put it in the valve and it failed. Surprise, surprise. Replacing qualified cabling with standard wiring, failing to restore seals or wraps, using incorrect fasteners. That's a big one. Or failing to update documentation after maintenance. So all those errors can make equipment appear functional during normal operation, but unavailable during accident conditions. So overall, this safe work depends on planning, verification, communication, configuration control, and our Lockout Tagout system it's also a system, protects workers from hazardous energy. Work controls ensures that maintenance is planned and authorized. Pre-job briefs and human performance tools reduce human error. The configuration management ensures the plant matches its design bases, and the EQ program ensures safe equipment can perform in accident conditions. The examples we talked about here, verifying zero energy, replacing equipment with the appropriate EQ equipment, safety-related equipment, all these things, the verifications, the use of the locks and the tags, all these show how our programs support worker safety, plant reliability, and basically trying to keep you safe. All right, so we are at the end of the presentation. You're going to review the lab activity and come prepared to jump right into the Lockout Tagout Verification Lab. So for the lab, review the tagout, follow the directions on your lab guide. You're going to do your verification and determine if the equipment is in the required condition, whether discrepancies exist, and whether maintenance can safely begin. And you're going to be doing this all through verifications. So some of those things matter, like we talked about in the fall when we did components. There was all that stuff about valves, remember? Then there's rising stem gate valves, there's globe valves, there's ball valves. And so you were expected to understand and retain all that, because you are going to walk down a tagout, do a verification, look at a valve, and try and determine what position it's in visually without operating the valve. So yeah, you're going to try and determine, can we do work? Does this tagout that I'm giving you, is it safe? Is it all good to go, safe to go to work? Are there discrepancies? What would need to be fixed? So yeah, all right. I'm looking forward to seeing you at the lab. Have a good one.